I'd like to acknowledge a few sponsors. First of all, the food that we are enjoying for lunch was paid for by EA. Dan works for EA Engineering. And for the record, EA has been a sponsor for a good number of events related to this work. So we greatly appreciate the lunch. Okay. The second item, some of you traveled on public funds from NOAA. So also we acknowledge the support from NOAA for travel. And the third one, and the most important one, also very important, like the rest, is ASCE. We are using the space in here for free. It is paid for by ASCE. Thank you, ASCE. Did I leave anybody? And the help of Megan and Erica. Thank you so much for all your work. All right. Okay, with that, we are ready for the speaker. Joe Barsugli will talk about. It's based on the work of the ASCE NOAA Task Force, and he will be providing some perspectives related to climate data and information. I'll leave it to you, Joe.
Thank you, Bilal. It seems like given the questions that came up this morning, this talk will maybe even raise more questions and hopefully answer some of them. So the title of this was originally something boring about implications of using global warming level, this and that. But since it's a lunch talk, I decided to pose it as a question. Do global warming levels solve climate uncertainty? And this really directly addresses the 3 degrees Celsius planning target that has been proposed for, hang on a minute, we have black slides here. And I want to say that this is really a compendium of ideas that have come up through work with the task force. Many people, I don't mention Don Scott there, but of course I should, because he's the one who came back to our group and said, we're going to decide on 3 degrees. So let me go to this is the, actually good. What did it is tricky. Use there. So what I hope you learn is lunch and learn session. So I hope you learn what a global warming level is, how it's defined, roughly how it's been used. Where are we now in terms of global warming? What is the climate science basis for using it? Why do you use this instead of scenarios or in addition to scenarios? The center of it really is talking about what this means for the uncertainty about the future. And I'm going to say the message up front, it doesn't get rid of uncertainty about the future, but it does, word I'm using is refactor it. It makes it a bit more tractable by splitting it into 2 parts. I want to talk about some of what I see as some of the potential benefits of using global warming levels instead of choosing scenarios and models. And then finally, some cautions about drawbacks and potentially cases where it's not appropriate. Now, I'm going to cover a lot of technical material here. There will be a quiz at the end. But first, a little motivation. So you've seen timelines. You saw a little bit in Dan Walker's talk about the timelines of climate modeling. So let me just present, there's an intricate process within ASCE for standards development. There's an intricate process within the climate science community here. I'm starting in the center with the CMIP process, the Coupled Model Intercomparison Project process, which is really the core of what climate modelers do to support these global assessments and national assessments. This is what the many modeling centers do. CMIP 6 was what we're dealing with now, but this is the plan for CMIP 7, which is already underway. And I've circled in red these proposals for their new emissions scenarios, the scenarios going forward. And that the proposal was just submitted. The comment period ended, unfortunately, so you can't really make comments on it. But just to say, that's where we are in that process. These get, again, run through the climate models and downscaled and such. And then, of course, starting in, after that, there'll be a CMIP 8 if things go as they have in the past. So I'm just going to put a big balloon over that saying CMIP 7. But where does this used, right? It is coordinated with the IPCC assessment reports that come out roughly every 7 years. So the next, we're dealing with assessment report 6 or AR6. AR7 is going to come out sometime towards the end of the 2020s. The model runs will probably be done a year or two before that. And there's a sort of a new process within IPCC that's been done once and will be proposed every 5 years, what they call the global stock take. And I only mention that because when we talk about what are our current policies globally leading towards in terms of temperature, the global stock take is very important because it basically goes around region by region, country by country, and says, what are policies doing now? I don't want to belabor that, but to say that this will be essential going forward when you think of 2034 and beyond. Now, this got a little bit darker to read than in my original, but this also feeds into the National Climate Assessment process. The U.S. National Climate Assessment by law should be approximately every 4 years. NCA 5 came out in the 5th one. National Climate Assessment 5 came out in late 2023. NCA 6 by that process would be roughly 2027. And NCA 7, 2031. So when you're talking about codes, it's codes, when standards become codes through IBC, through local adoptions, in the 2030s, we will be on CMIP 8 and NCA 7. We will be 2 cycles ahead. So how do you deal with it? This can be overwhelming. It's overwhelming for climate scientists, let alone the people who use the data. So this came out of this was just the cover of our workshop report there. So you've seen enough of that, but out of the last set of workshops really came out some overarching concerns. And really, how do you characterize future conditions in a way that is, number one, scientifically justified, 2, usable within the capacity of practicing engineers and standards developers. So basically straightforward enough to be adopted into engineering standards. And I would argue the issue of communication came up a lot, not just communication to engineers, but communication of engineers with their clients, particularly about relative levels of risk. What are you getting for adapting to a 3-degree world, for example? And in my view, you need to have a way of defining these standards and approaching the climate science in a way that is durable, meaning that we develop some method now, and that this method, at least in form, if not in detail, will be something that will get you through the next cycles. And climate science moves forward, as I've shown. I mean, the long life cycles of standards and climate science mean that you need to come up with a way that's really focused on the non-stationarity of information, not just on the stationarity of climate. So what I propose is that you define as many things as possible in terms of physical quantities. Things like 3 degrees Celsius is something we can estimate from the physical world, as opposed to, for example, individual scenario names, for example, the RCP 8.5 that has become these SSPs, 585 or 370. And then in the next iteration, they're going to be named something completely different, and their conceptualization will be different. So some of the options going forward are to just use a traditional emission scenario time period way of going about it. That will always be the basis of underlying data that comes from the CMIP process. It's been proposed also to use what's called a carbon budget. You'll see this a lot in global mitigation talks and global mitigation work. Carbon budget is how much more carbon can we emit, carbon or equivalent can we emit to the atmosphere, and before we reach a certain level. But I want to focus on this global warming level. For example, a 3 degrees Celsius global mean temperature above pre-industrial in 2080, 2100, end of century. So what is global warming level? Here's where I really want to come back to the basic topic of, the basic facts that I believe will help you get through discussions about global warming level, that I'm hoping we can build a common understanding, at least about what things are. So global warming level is the change in globally averaged temperature at or near the surface relative to a baseline period. So this is a map. This happens to be from one of the NASA global surface temperature data sets of a temperature anomaly. This happens to be relative. Unfortunately, I can't get maps relative to the standard baseline. This is from 1950. But typically, we use an 1850 to 1900 climate baseline. It's not quite pre-industrial, but it's early industrial, and there wasn't a lot of change, at least in our models, between pre-industrial and the late 1800s. Other baselines are used, but when most people talk about global warming level and a lot of the big users of it, like the IPCC, it'll be an 1850 to 1900 baseline period. But baseline shifts are easy. It's just a single number. You just add or subtract whatever the difference is in the observations. If you're using a later baseline, you can add or subtract whatever half a degree or a quarter of a degree, depending on how much warming has occurred. But smoothing is necessary. You can't just take an annual average temperature. You actually have to do some sort of smoothing. Otherwise, you get random weather effects. El Nino affects the global temperature. So typically a 20-year moving average is used, but other methods are possible. I'm going to show you one here. This is from NOAA's Climate at a Glance, which I go to all the time now. Global land and ocean temperature. It's an annual average, January to December for each year. And it has a smooth time series put through it through a what's called a local regression smoother, a low S smoother. I really prefer this because it handles the endpoints where we're on a trend better than, for example, a 20-year running mean, which would be backward looking. Now, as you notice, their baseline was 1900 to 2000, I believe. So I had to do, a baseline adjustment here. As you can see, 1850 to 1900 is about 0.2 Celsius lower than their long-term mean. But where are we? We're about 1.2 Celsius, maybe 1.25 Celsius above that baseline. So Don was saying, 1.3, 1.2. This is where we are with this sort of smooth estimate. We have ups and downs. I mean, last year was extremely warm for a number of reasons. Reached 1.5 or 1.7 even on monthly timescales. But when you smooth it out, our estimate is about 1.2. Now, this is, when you look at a 2 degrees Celsius world to plan for, we're more than halfway there. So where's it being used? I mentioned IPCC assessment report. It's a very nice way to look at increasing levels of forcing without having to get into the details of scenarios. National climate assessment, as Russ showed. One important place for engineers now is this interagency sea level rise technical report, which doesn't use it in great depth, but it uses it in a way that could be very useful. Another place in the literature it's being used is non-stationary extreme value analysis, where you use the global mean temperature as a covariate rather than time. And also, I finally mentioned the ASCE 728 Future Conditions chapter. So where might we be heading? And this is what gets to the question of why 3 degrees. Now this is, I can only present the evidence that I'm familiar with. Most recently, why 3 degrees seems to be a reasonable estimate given the amount of, given the implementation of policies that have been adopted around the world by many different countries. Of course, policy is not global. Policy is national and local. So the IPCC Working Group 3, which is the report that deals with mitigation, reduction of carbon, and estimates of that sort, estimated that under the 3-7.0, and the 7.0 is a measure of radiative imbalance, so watts per meter squared imbalance in the climate. So the higher that number, the more forcing there is. 3.3 SSP 3-70 had a 78% chance of exceeding 3 degrees Celsius. The 4.5, the lower one, which they called moderate action, which would require something more than current policy, has a 29% chance of exceeding 3 degrees Celsius. So you put those together, and you pretty much get that a 3 degrees Celsius sits in the middle of that range. A more recent estimate, and this is following work, and that Mari was mentioning that this was work that was done through, this comes from a site called Climate Action Tracker, but it's also done as a result of what happened in the last stock take, where the policies were much more clearly delineated. You can see in this blue bar at the left, it puts 2.7 Celsius as kind of the median, the central tendency estimate, and 2.2 to 3.4 degrees Celsius. But I'm a little cautious of these low estimates. There's a group of scientists who are a little worried that when you actually take these, you're not taking into account the surprises that could happen in the climate system, that perhaps some of the models that show a stronger climate response are keying into something that we should be, at least from a risk management point of view, being looking at. So, you could take 2.7 as an estimate, but I would argue it's itself is a conservative estimate. And of course, it requires the implementation of policies that we have to continue. So what's the justification? Well, for a lot of this is a direct quote from the IPCC assessment, but it really is supported by a lot of science. For many indicators of climate change, seasonal and average annual mean, extreme surface air temperatures, precipitation, etc., the changes are well estimated by the level of global surface warming, independently of the details of the emissions pathway and what caused the warming, or at the time at which the level of warming is attained. Now, it's not completely independent. If things happen tomorrow, if you quadrupled the CO2 in the atmosphere, things would. But given the typical types of scenarios that we think are realistic towards the end of the century, this statement is surprisingly robust. And here's an example that you can get from the IPCC's interactive atlas, if you like. For Eastern US, the lowest annual daily minimum temperature, so the coldest day of the year at nighttime. Over the Eastern US, you have global warming level along the x-axis and the coldest day of the year on the average coldest day of the year on the right. And you have a bunch of climate models and scenarios all mashed together here. What you can see is when you look at these in terms of global warming level, they line up quite well. You see something like a 2-to-1 ratio between those two. For 4 degrees of global warming above pre-industrial, you have about 8 degrees of the minimum temperature rising over land. What does tend to happen is that the scatter of these points, when you look at them in terms of global warming level, is considerably less than when you look at them in terms of time. Certainly for things like temperature, which are strongly related to forcing. Let's look at this again from a slightly more detailed perspective. Again, from the IPCC, but this shows how you get this. On the left are a bunch of climate models from 2 different emission scenarios, looking at the global temperature histories from many different models. The higher emission scenario in the brownish color, and the lower one, quite a lower one, SSP 126 in blue. And there's a 2 degree, in this case, 2 degrees Celsius line, and it reaches it at different times in this century. But you can just take what the models are doing at those little points defined on that horizontal line, average them together, and you get the kind of graphics you have on the right. So for temperature change, you see just a coherent increase in the pattern globally as you go from 1.5 to 2 to 4 degrees Celsius. Same with average precipitation change. You see in most places a very coherent pattern consistency. Even for things like soil moisture, you also see for many places, although if you actually look in detail, it's not quite as coherent as with the others. An important caveat: there are slow variables, things that are far out of equilibrium with the climate. Global sea level being the biggest one, and that tends to have the rate of change of that quantity scaling with global warming level. It makes sense. The warmer it is, the more melt you get, which is the rate of change of sea level. The warmer it is, the more transport of heat to the deep ocean, which expands, which is a very slow process. So for something like sea level rise, with cumulative effects over the century to century and a half scale, you need both a warming level and a time frame. Hence, Don's proclamation of 3 degrees by 2080 or 2100 by end of this century, basically. So to keep that important, things like deep aquifer recharge, which are slow, might also follow something like this. So This is the core of the talk about uncertainty. And it's a little complicated. And it's a little complicated because this is turned on its side. One of my favorite graphs from Rob Wilby, a wonderful UK, who's expert in hydrology impacts of climate change. Basically, the cascade of uncertainty. You have, the future society and emissions scenarios, climate modeling as you go from general to specific across here. At each stage of it, when you do this, what used to be called top down, when it was turned 90 degrees, it adds to the uncertainty. And this has led to a lot of paralysis of action, simply because people are overwhelmed with uncertainty. I mean, the uncertainty is real. I mean, it's the future. As someone said, someone told me, well, you're predicting the future. Of course, there's uncertainty, right? So, the typical approach is you choose emission scenarios, you choose an ensemble of climate models, perhaps downscaled to regional values, and then, either apply some sort of downstream model calculation, like a hydrology model, or something else to get design values. So the way I view this sort of mathematically is you have the probability of the emissions scenario, which might be qualitative, and then you have the probability of a local response given the emission scenarios in a set of models. What we're doing is intervening in the middle and saying, well, for 2 degrees Celsius warming, we have a smaller envelope down there. For 3 degrees Celsius, we have a higher level of risk, but roughly the same spread. And for 4 degrees, we also have a higher level of risk. So it breaks up this uncertainty mess into smaller triangles. But as Don will also point out, it puts a lot of all the global effects, the policy effects, and also the global sensitivity of these models on the left side of that line. And it puts all the regional and local effects on the right side. And I would argue we have a fairly good handle on the regional and local effects. If I tell you a 3-degree world, I could ballpark a number of estimates from physical principles. There are a lot of details that need to be worked out, some very important ones like the subdaily precipitation. But I would argue that we're getting a fairly good impression of the uncertainties, but also the regional impacts on the right side. The left side, of course, is going to be continually evolving according to policy and according to perhaps the discovery of some that some of the surprising feedback, such as permafrost and things melting and methane released from the ocean, might be stronger than we thought. But that's the left-hand side. The right-hand side, I think we have a pretty good stable understanding going forward. So this, I was surprised to find, was also from very deep in the IPCC reports, exactly what I was trying to get at, a simplified version of that. You actually concentrate all the different pathways that could lead to these global warming levels on the left, emissions questions and global responsive models, and you have the regional impacts questions on the right. So the way it works mathematically for me is you have a probability of emission scenario times the probability of a global warming level given those emission scenarios and models, all the global stuff and policy stuff. And then you have this separate side on the right, the probability of a response locally given that global warming level and models. And by separating this out, what I call refactoring the uncertainty, I believe it makes it more tractable. So potential advantages, I just said, in my view, it is a more tractable treatment of uncertainty. When Don came back to our working group in 2022, between our 2 sets of meetings and said, oh, well, SEI has decided as this target, Mari Tai and I, who were on this working group, breathed a sigh of relief because it simplifies the discussion beyond belief. We don't have to get into arguments about which scenarios. It also simplifies the idea if you want to do something else, well, okay, we'll make it 2.5 or we'll make it 3.5 if you want to be more risk averse. But it really, our experience has been that one of the hardest things when you go through adaptation practice are the arguments you get in over scenarios, or even just the understanding of what they are and what they mean in terms of risk. There's no need to choose explicit policy pathways. It recognizes that multiple emission scenarios and policies can lead to similar future conditions because the climate models have different sensitivities to those. It's a physical quantity. It will outlast the specific scenario names. It can be related back to sets of models and will have to be for most adaptation work. We'll have to choose a set of models or some analysis of those climate models in order to actually come to these 3 degrees and 3 degrees or 2 degrees or 4 degree worlds. Many hazards scale with increasing global warming level. They do with increasing emissions as well, of course. I argue that it also helps you, like for those who are planning for deep uncertainty, like planning beyond 2100 when there aren't climate model runs. Well, a 3-degree world, the precip extremes in that in 2150 are going to look a lot like, not exactly like, those in a 2100 world that's at 3 degrees. So it allows you at least to get a sense of what of how things might what it gets you to. you're kind of in dealing with a 3-degree world, no matter when it happens. Now, we just happen to think that the end of the century is a reasonable time given on current policies. The last thing I really want to talk about here is this third to last bullet here. It allows alignment of climate hazards from disparate sources when different approaches are taken. One thing that ASCE 728 has really brought home to me is a lot of the load subcommittees work with different data sources, and often that's necessary. We don't have one unifying, downscaled, all the way to engineering practice version from all the climate models. You might be using different subsets of climate models, different methodologies. You might be using combined observations and models. You might be using, simplified models, as is done with some of the hurricane wind work. And I'll come back to give you an example of that. But I also want to say, it doesn't always work. This is the same scatter plot, total precipitation in a place near and dear to me, the Colorado River Basin, from all these CMIP models. And you can see there's no real relationship between global warming level in these models. Now, I'm not taking this all the way to applications, but in these models, there's really no relationship. Well, there is a relationship here, actually, because as you go out to higher warming levels, there's greater uncertainty. So by actually looking at a global warming level, you can argue that you may have at least conditionally reduced your uncertainty, keeping in mind that you have actually set a condition on that. Nonlinear effects, rapid transitions may need special treatment. Things like snow and ice, you may have to be more careful. Particularly, you may want to look at temperature and precip inputs into snow and ice rather than the snow itself. So the time evolution, certain places with snow might get, you get more snow load because of increased water vapor before the temperature makes it not snow anymore. Regional anthropogenic forcing is important, things like urbanization, land use, black carbon, aerosols, particularly in other parts of the world where aerosols are black carbon. So one place it's used is in the recent 2022 Interagency Sea Level Rise report. Billy Sweet might be on the call, who was the lead author of that. What they really did is they didn't make it the prime guiding principle. What they did is they took global warming levels and made their scenarios consistent with them. And so this was, I would argue, relatively low cost as far as implementation version that gives you a lot of power from this. I don't want to go too much into this, except they have a really wonderful table. And I will say, well, how would you use this table? If you were trying to adapt to their, let's say, intermediate to high sea level rise scenario, which would be in the second row there under the red circle, what else would you do? I mean, they have sea level rise scenarios that are not explicitly derived from global warming levels. Well, this table tells you which global warming levels these are consistent with. So if you wanted to use that scenario, you might go up and say, oh, I'll get other data sources from the 3 C world. So the stuff that what Dawn is talking about, 3 Cs by the end of the century, would be consistent, at least from a broad climate science perspective, with the intermediate to high sea level scenario from this report. And I say this not as it may sound hypothetical, but when I was at the Inspire conference, one of my co-panelists, Chris Lashley, who was there, and he said, "Oh yeah, I've done this. I needed some winds from projections of hurricane winds, and I found some papers that talked about the scaling of hurricane winds with global mean temperature, and therefore I was able to combine those for his project." And I just said, "Well, this is really an example of how powerful this approach is, and that it clarifies." It clarifies some of the physics behind this, even if it doesn't solve all the uncertainties. So I guess this was really my talk about that. The the first bullets are that. I mean, it allows you to say riverine flooding, precipitation extremes, question about how do you do those, how do you combine those. But are we there yet? Well, not really. Most climate data sets and downscale data sets still use scenario time as an integrating dimension. I guess I didn't mention that word. The IPCC uses the word integrating dimension, just meaning a way to combine things. And quite honestly, as I said, climate scientists are also overwhelmed by the plethora of models and scenarios. Really, in the last 5 years, we have come to use that as an integrating, guiding principle when we want to really synthesize the data. And so I think you should too. Atlas 15, we have asked them to use that as an integrating dimension, and we've gotten positive responses from them in the course of discussions with the ASCE 728 future conditions. And of course, the ASCE 728 process itself is going to be doing its best to get that information into the suggestions for using for future conditions. So what did I hope you learned? Here's the quiz. How is global warming level defined? A couple seconds to mentally answer that question. Global average surface and usually surface air temperature change above the 1850 to 1900 levels typically. Where has it been used? Maybe I'll take some shout outs from the audience. Where has this been used as an integrating principle? Sea level rise? Any others? ASCE 7. National Climate Assessment and the IPCC assessment doesn't use that exclusively, but it uses that as a way to present and synthesize material. And also, I think for non-stationary extreme value analysis, I think that's something I'm more interested in. It's not, yeah. What are we at now? What number roughly are we at? 1.2 to 1.3, yeah, probably is good. What is the climate science basis for this? Let me just let you think for that for a second, because it's a bit of a long answer, but lots of climate responses are near equilibrium on 20-year timescale, so they can be treated as if they don't depend on when that's reached. Basically, time for many of these things that we deal with, that you're dealing with, the hazards, the time you reach them doesn't matter. So this kind of erases that uncertainty, or it doesn't erase it, but it minimizes that uncertainty as best as we can. So using global warming levels does not necessarily reduce uncertainty overall, but the word I'm using is refactors it. It splits it up into digestible chunks. So it puts the policy and global scale response on the left, puts the local effects and impacts on the right-hand side, which I got a lot of nods when I was saying, I think we have a better handle on that than we do on the policy on the left. So I don't know how much time we have here. If we have time for questions. Excellent, because I wanted to leave time for questions, especially given what was going on this morning. So I apologize if I went through that fast, because I really wanted to open it up to discussion. So I've got some discussion questions here. But I really, at this point, and I'm hoping Mari can help me answer these things, because she also was one of those people who was just so relieved when ASCE 7 decided to explore this. There's two things I also want to say. This is fairly new for a major adaptation effort that's going to have very large impacts in terms of, in terms of the world, in terms of costs, in terms of benefits. So, how do I want to put it? Questions are really welcome at this point to make this more justifiable. And the second thing is, it's not like rerunning the climate model. So don't think this is like, oh, you have to spend billions of dollars to do this. It's really analyzing the data in a different way. Those are the only things I want you to know going into that. Questions? Sure. Shall we start online? Well, the one thing that made it work for ASCE 7 is that, typical service lives or design lives were on the order of decades, many decades. So you're talking 50 years but often 50 years with the understanding that these things will still be buildings will still be standing at 50 years. And you want some assurance that they're not just going to collapse in the 51st year, right? When climate goes crazy. So things that have multi-decadal timescales like this are probably very applicable to this. Some things, as I say, that have undefined or just really long lives might also be, but you might want to use a higher level if you have a less risk tolerance. I think it also works in the nearer term. And one thing they're going to be doing, at least I understand in Atlas 15, is doing a non-stationary extreme value analysis of historical data. And if you get a really good solid estimate of how the extreme value parameters are changing, of course, you could, in theory, extrapolate those as well in the near term. Or else combine with models in a certain way. And I know there's some talk of that in the PMP report that just came out as well. Obi's here, who is an author on that. And I just got to read it on the plane coming over. So that these methods are all aligning in that way. But I would be cautious for things that are things like snow and ice that have like a highly nonlinear threshold in them, that you can't just take the snow out of a climate model. I mean, we know that for those who do that work, you do have to think through the process.
And my question is about the definition. If you go back to the previous, so you have it as it's the global average surface temperature. There's interaction between the surface and the top of the surface. Can you comment on that?
Yes. There are a few papers out there that talk about the difference. Oh, the question was some details, which I did leave off the slide, about what does surface air temperature mean because of interaction between the actual surface, the surface of the ocean and land, and levels at which air temperature is typically measured, which is nominally 2 meters above the surface. Historically, we have very good data of air temperature measured over land and the temperature of the upper layer of the ocean measured from ships. So one way to construct this is what's called sea surface temperature plus land surface air temperature. When you do the climate models, it's somewhat simpler just to use surface air temperature over the ocean, which is more constrained than it is over the land. So surface air temperature over land and ocean gives you a reasonably good estimate of what our best observational estimate is. So keep in mind, the way we calculate this is constrained by the kind of observations we have that go back that far. It turns out that surface air temperature over the ocean changes slightly differently than the sea surface temperature, but these are on the orders, I believe, if I remember the paper, should look it up, on the orders of 0.15 degrees compared to the 2 and 3 degree temperature changes. So the answer is surface air temperature is a very good proxy, and it really is mostly what's used over land anyway. And so using that over the ocean does not change the picture. I don't know if that was like more detail than you wanted or less detail than you wanted.
Maybe bring it home. I mean, we are. Let's say if I'm interested in buckling of rails for our rail network for freight rails, right? And these are on the ground, right? So how would that? What's your thoughts on this?
So my thoughts on materials, and this came up a lot in our temperature session 2 years ago, is materials are really an energy balance of the material. And you will need sunlight, you will need infrared, you'll need wind speed to get the actual temperature of the material. Air temperature is only one contribution to that. So if I gave you like the ground temperature, would that help you in actually calculating the rail temperature? No, you could use the air temperature plus your model of exactly how the materials respond to the energy balance. And I mean, in our field, you really have to go with the data you have, which is rich measurements of surface air temperature, and then derive other things from that. More recently, of course, there's satellite remote sensing. And I don't want to get into too much detail of that, particularly since I am not an expert in that. But when satellite remote sensing tends to measure the actual temperature of the surface, at least through thermal IR sensing. So for current applications, you might want to use something like that. But the reason we use air temperature is we want data that goes back to the 1900 and before if we can, so that we can actually make climate and climate change statements. So they're translatable between them to some extent.
Yeah, I have one of the ways we make decisions in engineering is using cost benefit analysis, where you actually need to know the time progression in order to value future benefits and future costs. And I don't know how this method would work. It doesn't really give you that sort of pathway of. So I guess this maybe is more for the standards committee. They suppose they have to balance the costs of a particular standard versus the benefits, and how would they do that with this particular method? Or that's
No,
they probably don't have to do that for this next ASC 7, but in the future we may have to do that.
Well, I was trying to get language into there, but I think it may be in the commentary that says the 3 degrees Celsius in 2100 is really a climate that goes from the present to that over the course of the century. And then if you really are interested in the time history, you can back it out. You can say these are the trajectories consistent with that from the climate models. When you average them all together, you don't have a lot of, difference. It's either growing a little exponentially, linear, or perhaps leveling off. And if you wanted to get to that level of detail of analysis, yes, you could back out specific trajectories. But they're all going to look like something that pretty much increases for most of the century. And if there's a lot more action, they'll level off. If not, they'll just more or less linearly go through the century. So implicit in 3 degrees Celsius end of century is the trajectory from here to there. So Mari might want to suggest something. So
That would be the best comment.
Yeah, I was just going to suggest that in the same way as we can do attribution studies where we run the climate models to look at what the risk of an extreme event might be or might have been in a world without climate warming, and then we run it again to see what the changed risk is now. We could quite easily be doing the same sort of thing to support changes in adaptation and changes in design structure codes that economists could then leverage that data to have a look at and say, this is your quantified benefit of the changed risk, the cost of the alternative cost of failure or of rebuilding every time this heightened risk occurs. So.
let me add to that. Underlying this might be, for example, an annual, a time-dependent value of an exceedance, like a 1% exceedance value from now to the end of the century. And then you could work with that, for example, to do your risk analysis. But there's tiers of information that can be used. We're talking here mainly about tiers of information for minimum standards, but I know the work you do, you require more detailed time trajectories, and that also could be supported, but it would require more climate information, but still could be consistent through this physical principle.
Aren't we fortunate to have Joe Barsugli?